Maintaining the free blocks in your disk is as important as the algorithm for allocating the disk that we discussed earlier. When you delete a file, the blocks used by the file must be reclaimed by the file system. Or when you add more data to your file, the file system must add more free blocks to your file. We will look at several techniques for managing free blocks in your disk. There are two major techniques for free space management. The first technique is the easiest. It uses an array of bits or a bitmap. The second technique uses a linked list that chains your free blocks together into a long list of free blocks. For improved performance, the list can be replaced with a tree. In our illustration, we have a very small disk of 25 blocks, B1, B2 all the way to 25. The green blocks are unused blocks and the red blocks are used blocks. To keep the status of allocation in our bitmap, we have to allocate 25 bits. The number of bits will be the same as the number of blocks in your disk. And the bit 0 tells us that the block is free, and bit 1 tells us that the block is allocated. So the first two bits are 0 because the first two blocks here are free. And the next bit is 1 because block number 3 is allocated. With 25 bits in the bitmap, we have to allocate a total of 4 bytes. So 25 divided by 8 is 3 point something, and we have to round up. So the number of bytes would be 4. Let's look at the overhead of wasted space by allocating the bitmap in our disk. So if we have a total disk of size d bytes and the size of each block is s bytes, that means the number of disk blocks in our disk will be the total size divided by the block size, and that number will tell us the number of disk blocks. But since one block requires 1 bit in our bitmap, this number is also the number of bits that we have to allocate in our bitmap. To calculate the size of bitmap in bytes, we have to divide this number by 8 and round it up. And if you count the wasted space, we just divide this number by the total disk size. And if you do the math, then the amount of wasted space will be 1 over 8 times s. If you recall the link or chain allocation strategy, where blocks allocated to a file are linked together into a linked list, we can use the same idea to keep all our free blocks together. So let's say we have 9 blocks in our disk free, B1, B2, B12, 13, 14, 22, 23, 24, 25, and we can just chain these free blocks together into a long list. So in order to implement this idea, then we do have to spare a few bytes in each block to be reserved as a pointer to the next block. So when we need to look for n free blocks, we have to follow n pointers into our list. So the cost of searching for free blocks is essentially On. So how do we improve the performance? So if we can make the list shorter, it will improve the performance. So then the next idea is we can pack block numbers into one block, because we know that each block is not used, and let's say if one block is 512 bytes, and if the block pointer is a 4-byte value, that means inside each free block, essentially we can keep 128 numbers. So using this idea, then we can pack more numbers into the free block, and these numbers are essentially the free block numbers in our list. So this is what we have when we link the free blocks together. The diagram in the lower half of this screen shows you how we can pack more block numbers into the free block. So we know block 1 is free, and block 2, 12, 13, 14, and 22 are also free. So then we can keep these numbers into block 1. And the last number is essentially used as the next pointer to the free block. So inside block 23, we can keep the remaining free block numbers 24, 25. So the improvement that we gain from here is we can make the list shorter. Instead of 9 elements, now the list has only 2 elements. Actually, we can make another improvement. If you notice that free blocks are usually adjacent blocks. So in our example, let's say the free blocks are 2, 5, 6, 7, 8, 9, 10, and so on and so forth. By packing the block numbers into the free block, we can keep this long list of free blocks into only 4 blocks. So let's say in block 2, the first free block is block 2, we can keep the next few numbers 5, 6, 7, 8, and so on into the first block. And the last number here will be the pointer to the next free block. And inside block 11, we can store the next few block numbers. So you can see that this long list of free block numbers can be recorded only in 4 blocks. But we can take advantage of the adjacent numbers in the free blocks. So you can select 3 groups of adjacent numbers, 5 to 11, 34 to 40, 81 to 85. So instead of using an enumerated list of blocks, I can replace this group with a range. So I can start with number 2, and then 5 to 11, and then 34 to 40, 64, and then 81 to 85. So we can see from this technique, we can make the list shorter if we replace adjacent blocks with a range. So to make everything looks like a range, then we can replace the singleton like 2 into a range like from 2 to 2, and 64 is now 64 to 64, and so on. So then now each number is now a range of 2 numbers. Alternatively, instead of using the range from start to end, we can also use a counter. So in this case, we have 1 free block starting from block number 2, and we have 7 free blocks starting at block 5, and we have 7 free blocks starting at block 34, and so on and so forth. So using this last technique, then we can keep a pair of number into our block. So now you can see that the pair 2, 1, 5, 7, 34, 7, and so on can be packed into the first block. So we start with block number 2 because block 2 is the first free block, and when we need to link to the next free block, then we're going to use the last item in our free block as a pointer to the next free block, and you can keep the rest of the free block information as a pair, and you can keep going. So what is the improvement? So if you look at the original list has 25 numbers. So if you keep these numbers individually in a free block, then the length of your list will be 25. And the improvement that we can make by packing the numbers together, that will make the list shorter from 25 to 4. But by using this range for adjacent blocks, we can make the list shorter, even shorter. So the improvement is from 25 elements to 4 elements to 2 elements. You know that searching a list will cost you ON, and to improve the search cost, you can replace your list with a tree. So now let's say all the free blocks information are encoded as a pair, block number, and count, as you see in here. So using a list, the search cost is ON. You can keep the same data in a tree instead of a list. Essentially, this tree keeps the same information as the free block you see here, and that will improve the search cost from ON to log N.